Okay, so this is the last lecture for the class, and I'm sure that you've got a lot of other things going on as well, so thanks for showing up. Today, this is, as I said last time, these two lectures are not part of the course syllabus, they're not on the final exam, they're more looking to the future. And in particular, what I want to talk about today is some kind of studying I did over the past year about how the electronics industry, what we now call the semiconductor industry, but it might be something different in the future as new technology comes along. But what directions it's going to head, and will we be able to assume the kind of progress that we've come to know and expect over the past several decades? So in particular, and this is important for obviously for people involved in ECE, but also for people involved in computer science and software, because the fact that we have this massive collection of computers, data centers, powerful cell phones and things, obviously the software people are important to that, but the reality is it's the hardware base that makes it possible. So it's really an important thing, even for software people, to have a fairly decent understanding of how the actual systems work, what their technology is, and what's that going to look like in the future. So in particular, we've been enjoying the benefits of what's commonly referred to as Moore's Law. And Gordon Moore he's still alive, and was one of the earlier pioneers in the semiconductor industry. He worked for William Shockley, who's one of the inventors of the transistor, and there was a company called Shockley Semiconductor that Shockley set up in the Bay Area in Palo Alto in the 1950s somewhere. And then he and a group of them left because Shockley was such a jerk, and found a home at an existing company called Fairchild that did things like aviation electronics, and set up Fairchild Semiconductor. And so that was really the start of Silicon Valley from the silicon perspective. Actually, they were using germanium at the time, but what we think of as Silicon Valley really got its start there. So he was the head of the research part of Fairchild Semiconductor when he wrote an article for what's really just a trade press magazine, electronics magazine. We wouldn't consider it a very important publication these days, but back then it had some fairly leading articles. And so he wrote an article, and this is in 1965, so almost exactly 50 years ago. And what he had done was he just sort of eyeballed what his company was able to do in terms of building the very new semiconductors. And it was the very, very early days of integrated circuits when you could put multiple transistors on a single chip. And what he recognized was there is sort of a curve of that on this axis it's how much does it cost per transistor to manufacture a system. And on the right-hand side, it's how many transistors there were on a single chip. And what he observed was there's sort of a sweet spot. And if you're to the left, you're not putting enough things on the chip. And so you have too many chips, and it costs a lot to connect them together. And you're not making use of the technology. And if you go too far to the right, then you're trying to squeeze more on that chip than was economically feasible at the time. And what he also observed was, and this is 65, remember, so he was basically projecting from 3 years worth of data, that curve was dropping. And so this sweet spot was shifting to telling you what's the optimum number of devices to put on a single chip, from like 20 here to 50 there, and then he projected out and said, well, gee, by 1970 we should be able to get 1,000 devices on a chip. And that was sort of just a prediction he made, and then that became known as Moore's Law. And that name was not made up by Moore, but by actually a professor at Caltech. So what we now know of as Moore's Law was really started with this prediction. And two things are worth noting. One is it's a technology prediction. It's based on what this company and other companies were able to do. But the other was an economic one. It was saying, if you want to make the best use of this technology and get the most sort of electronics for your dollar, then you should be following these principles. So, and that combination is actually quite important. So I went off and found a Wikipedia page that lists a bunch of different chips for microprocessors and other types of processors that has the both their chip area and how many transistors were on that. And I mapped it out. So it starts, the first microprocessor was called the 4004, made by Intel in 1971. And up through here, you see that I sort of partitioned these into different types of processors. So a desktop processor would be like what you'd have in a PC. And they sort of drove the industry for this middle part of the time. Embedded systems are chips that aren't designed to be computers that you're using as computers, but they're inside of something. For example, the earliest microprocessors, the 4004, was created by Intel to run a desktop calculator built by a Japanese company. They came to Intel and said, could you make us some electronics to implement this? And somebody within Intel had the inspiration to say, well, if we just implement this as a microprocessor, then we can write the code to implement a desktop calculator. And it's what they call a 4-bit microprocessor. So you're used to 32. Imagine 4. So the word size is 4. And how do you do that? It's actually, you have to think about how you even do that. But that's what it was, a 4-bit microprocessor. So anyways, embedded systems sort of, some of these were really a pre-PC era, and then these diamonds are ones that sort of drove the PC era. And then the yellow are more recent graphic processor units, which are some of the biggest, fastest chips out there. The X's are ones that are really server class machines, for example, the SHARC machines, and aren't designed to be inside of a big computer room. And down here, for example, these blue ones are actually for cell phones. But this is not a scientific sample. It's just ones for which I could find the appropriate data. Oh, and you might ask, why did you start in 1971 if this paper came out in 65? Well, back in 65, the technology was what they called bipolar technology, which is not a mental condition here. And it's very different. So the first microprocessor and all the successor ones are done in a technology called MOS, which stands for metal oxide semiconductor, which isn't a very useful name. But basically, chips since the early 70s have dominantly been using this technology, and the current one is called CMOS. So anyways, the interesting thing you'll see here is on this log scale, you'll see that this doubling every 2 years has almost exactly matched what's happened. So the gray line is if I just extrapolated from 50 transistors in 1965 and predicted they would double every 2 years, you get the gray line. And the black line is what I get running a regression on this data. And you'll see that their slopes are exactly the same. And what that means is the doubling every 2 years is absolutely true. And the black line, what it says is, well, actually, in the early days, they got ahead of the curve somewhat. So that the first microprocessor, for example, the 4004 had around, well, actually, I have the numbers. Actually, it had 1,700 transistors. So not too far off of what Moore had predicted for 1970. So anyways, that's the point. It's an amazing thing, this is held. And you might ask, wow, was like Gordon Moore the best forecaster of the future ever to be able to nail this number so precisely? And also, why do you call it a law? So there's a few things going on here. First of all, this is not a law. It's not a law of nature. It's not a law of our country. It's not a law of anything. It's just a statement that he made. But also, it's become a self-fulfilled law, meaning that because Gordon Moore, who was a very prominent person at the time, said this, and set his company in that direction, and he then went on to found Intel, by the way. He and all of his colleagues and his sort of burgeoning business have just been dedicated to the task of making this a law. So it was a prediction, but not in a sort of objective sense. It was a prediction by somebody who then motivated other people to fulfill it. So anyways, it's pretty interesting that just collect, and if you can collect all kinds of data, and you'll find this doubling pretty much holds. By the way, in general, you should, whenever you're looking at a semi-log plot, if you have a straight line, that's a sign of exponential growth. So what does this really mean then? It's hard for you to appreciate how much different the world of computing is today than it was even 20, 30, 40 years ago. So for example, in 1976, if you had a lot of money, in other words, you're Los Alamos National Laboratory, and you really wanted a big computer, you could buy it by basically getting a hand-built machine from a company called Cray, headed by Seymour Cray, who was one of the legendary people in the world of computing at the time. But this machine, as you see, all the numbers for it are way off what even I've got on my phone and what you have on your phone too, right? In terms of performance, in terms of density, this thing weighed 5,000 kilograms and used 115 kilowatts, whereas now we have these ones that are powered by batteries and fit in your pocket. And the other is numbers, that the whole life of the Cray, and this was considered an incredibly successful supercomputer, the first real supercomputer. In their whole lifetime, they manufactured 80 of them. And as you know, phones sell in the millions. So it's really very, very different world we live in because of the progress of integration. And so again, to put yourself back in 65, I'll date myself. I was a young person at that time, and for me, the coolest thing to get was a portable transistor radio, like this one, that would play AM stations. Okay, and now, today, what young teenagers crave for is the sort of latest consumer product of a high-end phone. So part of it is, if you looked at this, they even advertised that this transistor radio had 9 transistors on it. Whereas the chip inside of this is last year's, the iPhone 6, has, if you still have one, a chip with 2 billion transistors on it. And that's the main chip. There's about 11 chips in an iPhone, in a phone, by the way. But that's the main processor chip. So that's really the fundamental difference of why what you've got today is so different than what you could get in 65. So it's hard to even think about 2 billion transistors and what that really means. So here's an analogy. Imagine a transistor were the size of a grain of sand. They're actually a lot smaller than that, but just that's about the smallest thing you can think of sort of picking up and feeling. Then if you look at, here's this original 4004, had 2,300 transistors. I didn't have my numbers quite right. So that's, if you think in sand grains, it's actually, I calculated this out, it's 1/70th of a teaspoon. So just a very, very small pinch of sand is about 2,300 grains of sand. And nowadays, if you think of 2 billion transistors in terms of sand, that's about 200 pounds of sand. So if you go to Home Depot and you buy a bag of sand for your children's, for somebody's sandbox or whatever, it's about 50 pounds. So about four bags of sand is 2 billion grains. So that's sort of where we are today. We're at sort of it's the same as if you filled up a big paint bucket, 3 of them. Sort of that level we're at. So just to give you a sense of where we are. And so what I claim is, and this isn't just my claim, it's sort of self-evident, that there's this sort of virtuous cycle that drives the technology and the economics together. So in particular, the more things they can sell that have chips in them, the more money that gives for companies and more incentive that gives them to invest in research and development, to improve the technology, to buy. It's a very expensive capital equipment to run a semiconductor fabrication facility. And so that money comes from ultimately because they're selling this stuff. And because of that, they're then able to improve the technology, pack more transistors on a chip, make them run faster, reduce the power, all those good things. And then that's coupled with people who are good at product design and, of course, the software designers as well, to improve the product so that you want to buy more stuff, right? And that causes more sales. So this cycle is very important, that if it weren't for that looping around, then these improvements wouldn't be happening. So right now, the semiconductor industry is worldwide, and it's very much an international industry, is about $300 billion a year. So it's pretty big. And so what does that mean? Well, one is simply, let's just take the example of phones. That the iPhone, the first iPhone was in 2007 or so. And there's been 9 generations of them, including the most recent, which isn't shown in this picture. And so more or less every year, they come out with a new phone. And for example, this phone I'm carrying around is one I bought this fall, even though I had a phone from 2 years ago that was really okay. But I was sufficiently motivated to shell out the money, and now it's not hidden in our plans anymore, so I know this actually cost me $750. But I and many of my friends and people around the world did exactly that and created a huge pile of cash that infused Apple. And part of the reason Apple now is the largest company in the world in terms of market capitalization. So that cycle you can see here, you know, better products, more sales. You see that happening all the time. But underneath it all, what's driving that then is the ability to improve these products. So you've probably heard the other kind of stuff people are talking about is artificial intelligence, and will it basically eliminate all your jobs? And the famous sort of person behind that is a guy named Ray Kurzweil. So he proposed this idea they call the singularity, which is the day, I'll just describe it to you. You can tell I'm a skeptic on this. The day that computers become more powerful than humans, actually he's not the one who invented that term, then it's all of a sudden going to create this massive switchover where the computers are going to get smarter by teaching themselves to be smarter and soar off into infinity and making humans obsolete. That's the idea of the singularity. And part of the argument behind this is basically from Moore's law. So what Kurzweil did in this picture, and it actually started with some work by a person who used to be at the Robotics Institute here, was he plotted based on this, his measure was calculations per second per $1,000. So how much computation could you buy for $1,000? And he started it back at 1900 with mechanical adding machines and stuff like that. And added these plots. You see this was around 2000. And somehow, and this is an article of amazing plotting, he figured that this wasn't even a straight line. It was an upward curve. So an upward curve on a semi-log paper is more than exponential. It's like e to the x squared or something like that, right? So, but anyways, based on that projection and based on some notion of the relative power of human versus mouse versus insect brains, he came out with this projection that in 2030, roughly, computers would become smarter than humans. And if you just keep that on, computers would become smarter than all humans combined. So that, we can talk about this projection, and I'm sure you guys do at times too. But my point of it is, this argument is fundamentally a Moore's law argument. Right? The argument is basically, as computational power increases because of this continuing progress of technology, it's inevitable that, because humans aren't really getting smarter at a very fast rate, that it's inevitable that computers will become smarter than humans. That's sort of the argument. But it's very much based on this assumption that computer technology is going to continue to progress at an exponential pace. So let's now imagine, and this is something that you could be thinking about, is what will this mean 50 years from now? So if Moore's law looks back over the past 50 years, now let's look forward for another 50 years and see what that would mean and what it would possibly be. So here's one claim I'll make, is that whatever is the most important thing, it will be something that is in the hands of everyone, or is even more ubiquitous than there are humans on the planet, right? In other words, what I claim is the thing that will be the most important technology-wise will be what's the largest volume product. So I'm not sure what that will be in 2065. It certainly will not be called a cell phone, and it won't look like what we think of as a phone. After all, of all the things people own cell phones for, what do you use it for the least? Making calls, right? At least for me. So who knows what it will be? But I claim that, and this is a key part of this argument, that I claim it's got to be a portable, low-power system. So it has to be powerful computation, but it has to be physically small, and it can't draw much power. And that will be, and so it might be, the Internet of Things, where everything is networked together and there's computer chips or various chips in everything. Those kind of things would also have the kind of volumes needed to drive the market forward. So based on that, let's make that one part of assumption is, whatever drives the future, it's going to be something that is portable, low power, and low cost. Consumer grade, or something that you can afford to just sprinkle across the whole planet, or across the whole galaxy if we're beyond Earth at that point. So that means, for example, that it's not going to be a quantum computer, right? Unless people also make breakthroughs in superconducting, something that you have to cool down to near absolute zero requires a big room, a lot of equipment, and a lot of power, and a lot of things to manage it. So you're not going to carry that around in your pocket, I can promise you that. So all the people talking about a quantum computer, well, we can just rule that out. That's not going to be the most important thing out there. But it also, if you could imagine building this huge machine that occupies many acres of buildings, that's not going to be the most exciting thing out there, because there's not enough of those to sort of drive the market. And without that market, there won't be the investment in the technology. So it has to be inexpensive. And what, if we think of it in computer science terms, big O notation, it can't be, the cost to produce these things can't be very much. So for example, the chip that's in the cell phone, that Apple A8, costs somewhere between $10 and $20 for Apple to procure that from its suppliers, which are in Taiwan and in Korea. So they're not very expensive. That said, it need not be anything based on the technology we use today. As I mentioned, currently things are CMOS, and it's been some kind of MOS since the 1970s, so for a long time, but probably won't continue to be that way, at least not in the way we know it. And there's various other ideas people have had for future computer technology that beyond this, and some of it's being worked on here at CMU, and I won't predict what those could be, but they have to have these characteristics. It has to be inexpensive, has to be low power, has to be scalable. So that's my one assumption then I'm going to add is whatever it is, we're going to want a lot of them, a lot of transistors or devices of some sort. So what does that mean if we project that out in terms of how many devices are on a chip? Not how many transistors, but devices. So one great thing about semi-log plots is you can just extrapolate to your heart's content. So if we just run those two curves that I showed you before out, you get somewhere, we'll just pick a number that's sort of roughly in the middle of those two projections of 10 to the 17th. So 10 to the 17th things, devices, in a single integrated system of some kind. That would be what we'd be looking at. So how big is 10 to the 17th? Well, if we go back to our sand analogy, this is a picture I found on the internet of some young man in Brazil on a beach making a scale model of the Empire State Building out of sand. So my estimate is this is roughly something like 3 billion grains of sand in that thing. I didn't count them, I have to admit. But so think in terms, so something, roughly the same scale I showed you of those 4 bags of sand from Home Depot, something that's roughly comparable to what we'd get on a chip today if transistors were the size of a grain of sand. So what does 10 to the 17th mean? Well, if you actually built a sand model of the Empire State Building at 1-to-1 scale, right, then that's 1 million cubic meters. And then if you made 2 replicas of that, then and sum those 3 together, then you'd get about 10 to the 17th grains of sand. So of course, we're assuming this is going to be something a lot smaller than a grain of sand, but just to give you a sense of scale of how big a change that would be, going from a few billion to 10 to the 17th is a pretty big jump in terms of how many devices are involved. So let's figure out how could we make things, let's just say, well, let's just try running the numbers and seeing what would happen if we just took our current technology, which is more or less what we've been using since 1970, of putting a lot of transistors on a single chip. Actually, I happen to bring some toys with me today. This is a wafer. So this is what comes through a fabrication plant, and it's got typically about 700 individual, what they call die on them, that then they slice up and they put in packages. So these are some old packages, but now on your phone or your laptops, there's packaging in there. So they package the chips inside of there. So typically then, this is the current size that a company manufactures a die at. It's 30 centimeters, so about 1 foot in diameter. And you get about 700 chips on it. Chips are typically around 1 square centimeter. So let's just say, well, let's just take that technology, which over the years, these chips have gotten, the wafers have gotten bigger, the die have gotten a little bit bigger, and we've also been able to make much finer geometries on these chips. So let's sort of see how we've got this over history and what the projections of that would mean. And what the data show is that the way we've achieved a sort of doubling every 2 years in how many transistors were on a chip is, one, the chips have gotten bigger. They've doubled in size at a rate of once every 10 years. And also the geometries have gotten finer, that they've doubled in size or halved in size. Well, the density we can get as a result has gone by a factor of 2 every about 4 times in 10 years. And so you sum those up, you get 5 doublings every 10 years, and that's how you get Moore's law. So in particular, if you look at the earliest chip, the 4004, was about 12 square millimeters. So that's pretty small. And a modern chip is typically around a square centimeter. So, and this is actually to scale to a dime. There are some bigger chips out there, and they're not really blue. They just did this to make it look nice. But IBM, for example, makes a server where the chip size is almost 10 times larger than this processor. So you can get some pretty big die out there. But those are typically only, and also some GPUs can be pretty big die. So but those are used either in servers or in places where they're pretty specialized. For more portable battery-powered things, you have to go with smaller chips. So this is the data showing the area for these different microprocessors over time. And you can see that you're kind of all over the map. So it's a little risky to do any kind of extrapolation here. But this is where I got the number that it's doubled roughly every 10 years. The area of the chip. So if we project that out, then we get something of 173 square centimeters. So those of you who are metrically challenged, that number probably doesn't mean much to you. But just to give you a sense, like if I just extrapolated then, by the year 2065, I should be up to the Apple Model A59, because right, today's the A6. S. And so anyways, and it will, as we said, 10 to the 17th transistors, it will be 173 square centimeters. The problem with that is it's actually bigger than a dollar bill. It's about $2 bills in size, 173 square centimeters. And you're not going to fit that in your pocket, right? Unless you have really big pockets. So that is not the way things are going to work. We can't just keep scaling up area and expect that to happen. The other factor, which as we showed is more critical, is things have gotten smaller. And so the way I'll measure that is I'll take this measure I call L, the linear metric of chip density. I'll say the area of that chip divided by the number of transistors. And so one way to think about it is if the transistors were spread in a sort of uniform grid across a chip, then their spacing would be this number L. Of course, they're not. They're denser in some places and more spread out in others. But sort of if you think of this as a way to look overall at how closely packed are transistors to each other. And this is the curve you get from our existing set of processors. And you see this one really is a pretty strong trend of getting finer and finer geometries over time. And so the linear scale drops by a factor of 2 every 5 years. But if you think about the number of things, the density, therefore, goes by a factor of 4 every 5 years. And so that's, or equivalently, I've gotten twice as many transistors in a given area every 2.5 years. And we can see that again in practice, that if you measure out for the Intel 4004, it comes out to 72,000 nanometers, 10 to the 9th meters is this measure, whereas Apple A8 is 211 nanometers. So those of you who know about chip technology might know that the A8 was manufactured with what's called a 22 nanometer process. So when they measure, when you hear people talking about process, the actual fabrication process, and they give a number of, nowadays in nanometers, what they mean is the sort of closest spacing you can make two wires on a chip, the sort of finest geometry there. But this measure L is bigger because it counts for not just how closely you can pack wires, but all the other stuff. You have to put transistors there, you have to route power and ground and signal wires to them, and they have to be isolated from each other. So this is actually a more useful measure of the effect of spacing on a chip. Just to, again, if you're not so familiar with this kind of geometry, let's just give you some idea of it. So this range in nanometers then, between 1,000 and 1,000,000 then is sort of something smaller than a millimeter. Right? 1,000,000 nanometers is a millimeter. So 1,000 nanometers is a micron or a micrometer. And so this range, which is where semiconductor processing was up till 10 years ago, you'd call it the sub-millimeter range, and in this, it's in the sub-micrometer range. So just to give you some sense of what those scales mean, and I'll point out that it's pretty incredible to talk about something over 6 orders of magnitude in scale, right? That's, in the physical world, 6 orders of magnitude is a lot. So again, if you look at, here's some examples of things of how big is a micrometer, often called a micron. So things at the are almost visible at this scale. A human cell, how thick a piece of plastic saran wrap is, how thick a strand of spider silk is, gives you some rough number. And so this Intel chip from the 70s was somewhere in that range. And now if we look somewhere between a nanometer and a micrometer, and again, this is a log plot, so these things go pretty fast. So for example, all of visible light is in this range between 400 and 700 nanometers. And the spacing of transistors on an Apple chip are therefore closer than the wavelength of visible light. By the way, which makes for kind of a challenge for manufacturing. Something like how thick is a cell membrane, or what's the diameter of a strand of DNA, are down in just a few nanometer range. What they call carbon nanotubes, which people predict will be possibly a successor to transistors, their diameter, not their length, is 1 nanometer. So those are pretty small when you're getting down here. And nowadays, modern processes, they're trying to create features down in this range of 14 nanometers, for example. Okay, but we can do our plots. And if you just project out, you'll get down to this linear spacing of 230 picometers in 50 years. So what does that mean? How big is a picometer? Well, picometer is really small. In fact, if you look at the spacing between 2 atoms in a silicon crystal, they're about half of a nanometer. And if you look at the spacing between the 2 atoms in a hydrogen molecule, they're 74 picometers. So the main thing to realize is this ain't going to happen. There is absolutely no way that we'll be able to create systems where things are spaced only 230 picometers apart, right? Because presumably whatever we build is going to be bigger than a hydrogen atom or molecule. So, so this really is not in the range of physically possible. And that's one of the annoying things that physics has sort of gotten in the way of progress recently. So in particular, could we imagine then, let's just suppose we'll allow a chip, we'll say, let's let a chip be as big as 400 square millimeters, just about twice as big on a side as the current chip, current standard chip. That would still require this spacing metric of 63 picometers. Wait a minute, is that right? Yes, because I'm not allowed to make chips the size of $2 bills. So it requires even finer spacing here. And we saw that's just 63 picometers is actually closer than the two atoms in a hydrogen molecule, the two nuclei in a hydrogen molecule. So the answer is no, this isn't going to happen. This just plain is not possible. At least not, so we have to back off and say, well, what's our defect in our thinking? One is to assume that we're going to just take this current technology of two-dimensional things and just shrink it. And one reason we look at it that way, because that's exactly what's happened over the past 50 years. But we have 3 dimensions in this world, and so maybe there's some prospect there. So let's say instead, okay, let's imagine a little brick of stuff. And I'll just make up some numbers. I'll say it's 2 centimeters on a side and 5 millimeters high. It's almost exactly the same shape and volume as a stack of 5 nickels. And now let's just imagine, okay, how are we going to integrate a bunch of things? Well, presumably we're going to build it out of layers. And so let's just assume that there's about 100,000 layers worth of stuff. And those are what I'll call logical layers, meaning that there'll be about 1 million physical layers, because we have to have wires, and these, whatever we're building won't be just these totally flat things. Nowadays, there's a modern chip has more like 20 physical layers on it. So the point is that we'll have to have about 1 million physical layers worth of stuff to get 100,000 logical layers. But that would allow us a spacing on a linear spacing of about 20 nanometers. So 20 nanometers is a lot better than 63 picometers. Right? If we go back, 20 nanometers is up in here. So it's really, really small, but it's not beyond a physical possibility. Let's just put it that way. So you could imagine some technology that would give you that. So at least at some level, it's vaguely, it's aggressive but possible to imagine in 50 years being able to manufacture in a shape like that something with 10 to the 17th devices. But there's a few problems. One is actually the manufacturing, how we'd actually do this is no small thing. Another I'll talk about some is how do we do this and not spend an exorbitant amount of money doing it. And the other is a huge, huge problem of power consumption. How can we actually have a system that complicated and keep it at the limited energy level we have available? So let me go into that some more. So just as a sort of tutorial, the way these chips are made, and part of the reason they're so cheap, is it's sort of a photo process, meaning that every step of the way is done by putting some kind of material down and exposing it to a laser light, and then this material that you put down is light sensitive. And so there's a mask that defines how things should be patterned, and the light only hits where the mask allows it to, and that's how you get different shapes and things. And you can either add material or you can remove material by these masking steps. So nowadays, a modern chip takes about 60 of these steps where involving a mask and some type of either depositing something or removing something or shining a light on it or a beam of ions or some other process step to do it. So it's very complicated. The technology is quite remarkable. But what you could say is that even though there's a couple billion transistors on a chip, it still is a constant time process, some fixed number of steps, and it's done. And each successive generation, maybe the number of masking steps has increased a little bit over time, but roughly speaking, it's always a constant time operation. And it turns out that the bottleneck in this and the performance one is actually this photolithography, exposing the chip, the wafer, using a mask. And the way that's done nowadays is a machine called a stepper that basically is used to scan over the wafer and expose with a laser, sort of flashing as it goes, to expose the wafer to this mask. And so current day, that's done at on a size of about 900 square millimeters, so about this big a size, how much they can expose at a time. And the fastest steppers out there can do a whole wafer in 18 seconds, which is pretty good if you think of waving over this whole area, flashing and exposing it with extremely high resolution and very high alignment reliability. But that's sort of the thing that sort of limits how many chips you can run through a fabrication facility per day, is this stepper. And the stepper is the most expensive piece of machinery in the building, so you don't want to buy a whole lot of them. So that's sort of my point is that lithography is the expensive thing. So every layer we have to do, if we have to expose it using this technique, is expensive. And so there's no way you could do a 1,000,000 layer system using photolithography and keep the expense down to the range where it would be something you or I would be able to afford as a consumer device. As I said, a modern chip is somewhere between $10 and $20. So we're not talking a lot of money, right? If you increase that cost by 100, then people aren't going to buy it. Because if you think if a $10 chip powers a $700 phone, then there's a big multiplier in there. So there's various options you can imagine. One is what they call chemical self-assembly, where basically whatever you're fabbing sort of patterns itself, just like the crystals would in a block of, or something like that. If you can imagine various chemical processes where things just form into the particular shapes. So this is an area that's been tried and worked on for electronics for several decades and never really succeeded yet, but maybe that's possible. And another possibility would be some interesting ideas in working with multiple layers at once. So in particular, one technology that's really been able to scale into 3 dimensions are flash chips, and that's part of the reason why my phone has 64 gigabytes. I'm not bragging, I'm just telling you. My phone has 64 gigabytes of memory. Why is there so much memory, flash memory available on it? Flash, as you know, is sort of the storage of choice in a solid-state disk on cell phones nowadays, and so it's based on semiconductor devices. So, for example, this is an electron micrograph of a chip from Samsung showing how they are able to create a sort of 3-dimensional layering of memory cells. So basically every spot in X, Y, and Z here is a 1 bit's worth, actually 2 bits worth of memory cell. And there's some device there that can store it, and then there's ways that you can access it to either read it or write it. And they're able to do this whole layering, but by using only a fixed number of masking steps. So basically what they start off with is they build up layers without any masking, and then they put some masks there, and then they zap down, and they can sort of carve away using basically ion beams to carve down wherever the mask is and pattern things. And then they can pour various types of goop in there that will fill up these spaces. And so by some patterning only at the very top layer, they can actually create this three-dimensional matrix of memory cells. And they can now, the most recent technology gets about 48 layers, and there's projections that they'll be able to keep doing that at least through several hundred layers. So my point is that you can actually you don't necessarily need to do masking at every single layer to create a three-dimensional structure. Now, this doesn't scale in an obvious way to computers or microprocessors or anything with computation. It relies very heavily on the fact that the particular circuit of flash memory is very simple and fairly easy to build in this three-dimensional structure. But at least this is the kind of idea of what will have to happen if we're going to get this kind of integration. But here's the harder one, and this is a problem just in general. We're already up against serious power issues now. So if I look at a modern phone, it only draws, even when it's sort of working hardest, a couple of watts. Typically, when it's just, if you want to walk around, if you want to have the battery be good for a day at a time, it has to draw a lot less power than that. So typically, when your phone's in standby, it's only drawing a few milliwatts, so maybe 1/100 of a watt. But when it needs to, like you've just taken a picture and it wants to do some image processing on it, or you're taking a video or something like that, it can crank up to a couple of watts of power. So why can't it go more than that? One is, as I mentioned, is the battery, but the other is, if your phone draws more than a few watts, then you won't really want to walk around with it in your pocket because it'll be too hot. So, you know, just imagine a 25-watt light bulb if you put that in your pocket and walked around as far as the extension cord would let you. That wouldn't feel too good. So that limits the power. Isn't just battery. So even if we come up with better battery sources, the other thing is cooling. So contrast that to the human brain is actually pretty amazing as a low power system. So a human brain contains roughly 64 billion neurons, but it draws a few tens of watts. So there's reasons then that, so it's a higher powered thing than a phone, but it's still a very low power system. So high power, it's partly that it's a liquid cooled system. Your body's circulation system puts a lot of its work into keeping your brain from overheating. And your body's metabolism, for example, you guys sitting here, each of you are drawing about 60 watts. So you're like a 60-watt light bulb. But about a quarter of that power is powering the neurons in your brain. So it's a fairly big chunk of the human energy budget is the brain, which makes sense. But it's still more power than we're really going to allow in our portable devices if we don't want our pants to catch on fire. And now the crazy thing is, but wait a minute, I wanted to go up to 10 to the 17th of these devices, 500,000 times more, and I don't want to add any more power to this. So how is that going to happen? Well, it's certainly not going to happen with the technology we have today. That just can't possibly meet those. So we'll have to have some fairly radically different technology from a power perspective as well. And this goes also not just for portable devices, but even room size, building size computers. For example, right now the fastest computer in the US is at Oak Ridge National Labs. It's called Titan. The fastest in the world is in China. And both of them draw roughly 10 megawatts, okay, of power. So the high-end supercomputers. And one of the goals that the supercomputing people talk about is to scale up to what they call exascale, meaning the ability to do 10 to the 18th operations per second, what they call flops, floating point operations per second. So if you just took Titan and said, okay, we want to make it go 100 times faster, we'll just put more. So for example, Titan is built out of 28,000 microprocessors and 28,000 GPUs. So if we just crank all that up by a factor of 100, then you're talking close to a gigawatt of power. So, and just roughly, in rough terms, the entire output of the Hoover Dam would be enough to power a 1 gigawatt system. So, or a small nuclear power plant could do it too. But the point is, power is going to be a big issue for both portable things and for all of computing as we go forward. Okay, so that's sort of some of the technical challenges, a combination. But another is an economic challenge, is that it turns out that semiconductor business has become more capital intensive and harder to sustain. And so this is an example of all the companies that were able to manufacture chips at different physical sizes. So it's a little bit out of date. The latest chips are 14 nanometers. But you see that we're basically down to 4 companies in the world who have the wherewithal to manufacture state-of-the-art semiconductor systems. And these are, just to let you know, TSMC is Taiwan Semiconductor Manufacturer. They're huge in producing chips for other customers, basically, what they call a foundry. So other designs come in. So for example, TSMC historically has been the main vendor for Apple. For almost all Android phones are manufactured by TSMC. Intel, you know Intel, but they very much rely completely for their business on microprocessors and other things. They are, they only, with a small exception, only manufacture chips for their own use, their own company. Samsung, as you know, is in Korea, is a leading manufacturer. And a lot of what they do is produce chips for Samsung products. But they also are one of the biggest vendors of memory. They also actually, interestingly, manufacture some of the chips for Apple. So if you think about the phone business, who are the big competitors? Samsung, Apple. But Samsung actually builds Apple's chips. Apple has no manufacturing capabilities whatsoever. And then the fourth one is the one called Global Foundries, which is a company that sort of swept up all the second string players. And it's actually owned by the sovereign wealth fund of Abu Dhabi, so one of the United Arab Emirates. So really, if you're, you can say that there's 2 companies in Asia. One that's headquartered in Abu Dhabi, but it's actually physically, their manufacturing facilities are in the US, in Germany, and in Singapore. Intel, all of its manufacturing is in the US. Taiwan is, at least for the leading edge, all in Taiwan. And Samsung, they have a fab in Texas and in Korea. So anyways, my point is, this isn't very many. If you think of a $300 billion industry and sort of where we're betting our future on, to only have 4 companies really that are in the business right now is a little bit scary. And as you see, if this trend continues, things wouldn't go well. In particular, if we want innovation and progress to happen, we need competition. And if the number of companies drops too small, then the competition won't be as significant either. So these are interesting questions. Another thing that's making life difficult, and it's been making life difficult for the last 10 years, is what's sometimes referred to as Dennard scaling. And this is a term that you'll hear said nowadays, and just a few years ago, if you mentioned that term, people would have no idea what you're talking about, unless you were pretty heavy into chips. But there's a fellow named Robert Dennard who has had a long career at IBM. He actually got his PhD here from Carnegie Tech in the 1950s. And among other things, he invented the dynamic RAM. So DRAM, he's the guy. But he wrote a very interesting paper in 1974 that sort of sketched out why it is that by shrinking chips, life gets better. And it's a very simple model, sort of simple area, geometry, basics of Ohm's law kind of stuff that, that tells you what it's doing. But he said, imagine we can shrink a chip, all the features on a chip by a factor of some number, k. Typically, we either say 2 or the square root of 2. So if you can shrink in both x and y directions by a factor of k, and this is a big important and we also reduce the supply voltage to the chip by that same factor, then obviously we're going to increase the number of devices by a factor of k squared, right? But also we'll be able to make these run faster, and we'll be able to do it without requiring more power per chip. So if all this scaling holds, then we can get more stuff on a chip, run it faster, and not use more power. So that's sort of the principle of Dennard scaling. And that's really what was followed by the industry for from about 75 to about 2004. This is a chart that shows how technology progressed. So the top curve here is Moore's law, how many transistors were on a chip. This next curve down was how fast could a microprocessor go, running a single thread of execution. And you see it was following a sort of nice steady growth curve. What was the frequency, the clock frequency of the chip? You saw also followed this nice growth curve until it hit about 2 gigahertz. How many watts per chip? Well, it's kind of variable, but it was more or less, it was scaling faster than Dennard's scaling predicted, but still pretty reasonable. And how many cores would we put on a chip? Well, it was 1 for a really long time, and then they started adding more. So the main point to notice is somewhere, actually, it was right around 2005, things stopped progressing. Moore's law continues. It continues today. We can get more stuff on a chip than before. But how fast a given thread goes has not really improved much in the past 10 years. And that's why the Shark machines, which are already 5 years old, are actually pretty viable computers. The number of watts has leveled off not because that's the best thing computing-wise, but that's because you just can't afford to the cost, the actual electricity cost, as well as all the requirements for cooling and things that comes with increased power. And so that combination is the reason why we've gone multi-core, that we couldn't get improved single-threaded performance, but we could improve the number of transistors per chip. So what do? We just make more cores. And so, so some will tell you that Moore's law is already dead. in the sense that for a while there was this sort of miraculous, things just kept getting better and better every year because of Moore's law. And now we're already in an era that even though the transistor density part of Moore's law holds, some of these other performance factors have not improved. So it's already getting difficult to sort of use this technology to make things faster and more powerful. And so I'll mention, for example, part of the reason why this phone, actually I don't know how many transistors are in this phone, but if you think of 2 billion transistors, the model before that had 1 billion, you say, well, what are all these transistors doing? Part of what they've done is, and part of the reason they're able to keep the power down is a lot of what's on they call the chip now, it's not called a microprocessor, it's called a system on a chip. Because embedded on it will be a couple of ARM microprocessors, several graphic processing units to handle the video, the image processing, and other specialized pieces of hardware that are only used for very specific things. So for example, there's a JPEG encoding and decoding is directly integrated into hardware on this chip. There's actually some special logic for when you take panoramic shots and then you merge those all together, which I don't know about you, but I don't do that very often. But there's still some special dedicated hardware on those chips to do that because it takes a lot of power otherwise. So in general, if you can take some computing and turn it from software and migrate it to hardware, you get a big performance increase and a major power reduction. So they're putting more stuff on a chip, not to give you a more powerful processor, but to be able to do more stuff at lower power. So that's why these chips get more. So my point is that we're already in an era when the driving reason for Moore's law isn't so much to get raw performance out of these systems, but to give you more features of various sorts. Okay, so looking to the future then, as I said, you can look at since '65, it's been a very long set of incremental improvements to get from the chips of Gordon Moore's early career to where we are today. We got more stuff on a chip, vastly more capable, much more affordable, huge impact on it. But from a technology point of view, it's been a fairly incremental road to travel. We can see that that's not going to work in the future. We're not going to be able to scale transistor logic to the level that you'd need to keep this going. So at least two-dimensional semiconductor chips aren't going to carry the way. So there's sort of issues then, and you and your careers will be dealing with these, is will we be able to build systems of this complexity in a way that's commercially viable? Because if it's not economically viable, it's just not going to happen. And power is going to be a huge problem as we go along. And then, what would it mean if you actually had 10 to the 17th? I can't think of what possible capabilities this would give us that we'd actually want and use. But again, I don't think Gordon Moore would have thought back in '65. Actually, if you look at the '65 paper, I recommend you do. He actually did predict things like personal computers and cell phones, believe it or not. It's really true. So he was definitely pretty good. But for me, I can't predict what I'd have in 50 years and what I'd do with it. And then for more the software people, what will it mean? Will there be programming? We certainly won't be writing lines of code in C in order to power systems like this. So what will that mean for the future? Those are all big questions that you and this point of your careers get to look forward to. So I wish you the best in doing that.